So let's move on to the organic addition reaction to alkenes. You'll remember that alkenes with an E means that we've got a carbon-carbon double bond. So what we're going to do here is that in our carbon-carbon double bond, one of these bonds is going to be broken, and we're going to add our compounds, whatever it is, and X and Y in this case, are going to be added to the two carbons, and we'll end up with this structure right here. Now, there are two sorts of addition reactions we're going to look at. One is hydrogenation, which is we're going to add hydrogen to each of the carbons. The other is hydration. Hydration is water, and so we're going to add a hydroxy to one of the carbons and a hydrogen to the other of the carbons. So let's look at hydrogenation first. So here we have palmitic acid, and it's a cis, remember it's got a C, unsaturated fatty acid. That's a healthy fatty acid for us to consume. Now, when we add the hydrogen in the platinum catalyst, what will happen is our carbon-carbon double bond. I'm going to just draw a little bit of this molecule here. I'm just going to do from here to here. This goes on to something else. This has got a hydrogen and hydrogen, 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 onto the rest of the molecule. And there's a hydrogen here and a hydrogen here. And they're on the same side because they're cis. If we add this platinum catalyst, what we'll do is we'll break this double bond, and it'll be a single bond, and we'll add hydrogen, hydrogen, and we'll get this structure right here. As a side reaction, we will also get a trans palmitic acid. It's a product of partial hydrogenation. These are the trans fatty acids that are bad for us. Bad. They are the ones that they've been pretty much banning them from foods. They make foods more shelf stable, and so that's why they used to do this hydrogenation process. But they've been banned, and we don't have those much anymore. So, providing the products of complete hydrogenation for each of the products shown is just a matter of adding hydrogens. So, we'd get for this one, we'd get CH3, CH2, 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 CH3. All I've done is add hydrogen here and add hydrogen here. So for this one, we would get you just eliminate all the double bonds. And if we assume complete hydrogenation, this one we'd get OH. Make sure I get you on the, you can see me. I'm going to have to count my carbons here and make sure I've got the right number. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Well, that was just lucky. All right. So hydrogenation is not too difficult to draw because you just get rid of the double bonds. You add hydrogens. We don't usually draw the hydrogen, so that makes that easy. Hydration is the addition of water to the double bond. So one side gets hydrogen and the other side gets an hydroxy group. So we break the double bond, one side gets the hydrogen, the other side gets the hydroxy. We have an example here in the citric acid cycle. Here, the double bond between the carbons is broken, and it looks like we've added hydroxy there, hydrogen there. We do have one problem, though, as to which carbon gets the hydroxy group. With the hydrogenation, we didn't have to worry about that because we were adding hydrogen to both sides. But now we've got hydroxy on one side and hydrogen on the other. So what happens? Does the hydroxy get over here, or does it get over here? Or both, maybe. Well, in general, the carbon with more hydrogens gets the hydrogen. So if this is our compound, this side has 2 hydrogens, this side has 1 hydrogen. So the side with the hydrogens is more likely to get the hydrogen, and the one with only 1 hydrogen gets the hydroxy. So this is what happens. If we look back up here, this will not happen, because here we're giving the hydroxy to the carbon that has the more hydrogens. Okay, so the hydrogens like to party together, and so the hydrogen that's added would rather go with the other hydrogens so that it can party with the other hydrogens and leave the hydroxy to go on the other side. So let's do some examples before I leave you. So here we're going to hydrate this. We're going to need to add a hydrogen to one side and a hydroxy to the other. The hydrogen is going to want to go on the side with the more hydrogens. So this carbon has 1 hydrogen, and this carbon has 2 hydrogens. So the hydrogen is going to go over here. So let's write our compound, CH2, CH, and CH3, because we've got 3 hydrogens there, and we're going to put the hydroxy on that one. This one got the extra hydrogen, this carbon got the extra hydrogen, and this one got the extra hydroxy. So let's look at this one. Let's draw it first. So this is our double bond. We've got this carbon is going to get something, and this carbon is going to get something. We just have to decide which ones they're going to get. So let's draw in our hydrogens, and we'll draw them over here. Let's see. This carbon's got 4 bonds. 1, 2, 3, 4. This bond has 3 bonds, so it's got a hydrogen. We don't usually draw the hydrogen, but it's there, even though we don't draw it. The hydrogen, when we add it, is going to want to go over here. There's the hydrogen that's already there, and here's our new hydrogen, and our hydroxy is going to go there. So if we're going to draw this, we would probably draw it more like that. We don't usually draw the hydroxys. I mean the hydrogen. Sorry, I said that. Okay, so let's add a hydration to this compound. So this is our form. Let's put our hydrogens on this. We know that there are 2 hydrogens up here, 2 hydrogens down here. There are hydrogens over there too, but there's 1 here, right? And 1 here. So each side has 1 hydrogen, so it doesn't matter which side gets the hydrogen. Okay, so that's it for this chapter. You are done. Thank you for listening, and I will hopefully see you soon.